Summer 1940. Royal Air Force's Hornchurch Airfield in Essex. Two identical Supermarine Spitfires lie side by side on a concrete apron, yet the difference between them would turn the tide of aerial warfare. Squadron leader Desmond Cook climbs into the first aircraft, throttles up the Merlin engine, and races down the runway. The takeoff roll stretches 320 yards. The climb to 20,000 feet takes 11 minutes and 8 seconds. The service ceiling, where the air thins and engines gasped, tops out at 32,000 feet. Moments later, Cook enters the second Spitfire. The same Merlin engine, the same 8-gun armament, the same airframe, but a different propeller. This time the takeoff roll is just 225 yards. The climb to 20,000 feet takes only 7 minutes and 42 seconds, and the service ceiling soars to 39,000 feet. These dramatic improvements were not luck. They were thanks to 3 aluminum blades spinning faster, crafted from a design once dismissed as impossibly complex by aviation experts in America. This breakthrough sprang from the mind of Frank Walker Caldwell, a methodical engineer with an MIT pedigree, whose relentless devotion to numbers and engineering precision revolutionized aviation propulsion. His vision began years earlier in a Connecticut factory, where on a gray February morning in 1932, Caldwell stood before a gleaming 3-blade propeller mounted on a test stand. This propeller could change its blade angle automatically while spinning at 2,400 revolutions per minute, a feat never achieved before. The story of Caldwell's battle against conventional wisdom began amidst skepticism and industry resistance. His novel hydraulic governor system, designed to automatically adjust propeller blade pitch for optimal performance at every flight stage, was considered too complex, prone to failure, and heavier than traditional fixed-pitch wooden blades. Even celebrated aviators like Charles Lindbergh questioned the concept. Yet, Caldwell's quiet confidence stemmed from a career built on transforming assumptions into facts. Once opposing metal propellers before they became industry standard, now championing constant speed mechanisms destined to redefine flight. His vision promised aircraft with shorter takeoff distances, steeper climb rates, higher service ceilings, and better fuel efficiency. As the stakes rose in the early 1930s, with airlines like United and Pan American pushing for faster, more reliable aircraft able to conquer challenging terrains like the Rocky Mountains, Caldwell's invention became a lifeline. The Boeing 247's failure to cross mountain passes due to wooden fixed-pitch propellers underscored the urgent need for better technology. An ultimatum from airline presidents forced Boeing's hand: accept Caldwell's invention or lose orders. Caldwell's propeller used engine oil pressure as a hydraulic power source to shift blade pitch, working like a car's transmission to provide a low gear for climb and a high gear for cruise. Its feathering capability, reducing drag from failed engines, would later prove life-saving for countless bomber crews. Despite the industry doubts, rigorous testing proved Caldwell right. His designs increased climb rates by over 40%, extended service ceilings by 7,000 feet, and improved fuel efficiency significantly, transforming not just commercial airliners but ultimately military aircraft. The pilot's ability to climb faster, reach higher altitudes, and fly further would soon become a decisive factor in battles that shaped history. In the shadows of growing war clouds in Europe and Asia, Caldwell's propeller quietly prepared to tip the scales. By rewriting the very physics of flight, one determined engineer was poised to transform the fate of nations and the skies above them. This is the story of how numbers, perseverance, and mechanical elegance won a silent battle that paved the way for Allied air supremacy in World War II. The dawn of the 1930s was an era marked by cautious optimism and dogmatic tradition within the aviation industry. Engineers and executives alike clung tightly to the established ways: wooden propellers, fixed-pitch blades, and pilots manually adjusting settings mid-flight. To many, the idea of a constantly adjusting propeller that could adapt in real time to flight conditions was not just impractical. It was a dangerous gamble with lives on the line. Frank Walker Caldwell had spent decades challenging these assumptions. As the government's chief propeller engineer from 1917 to 1928, he had witnessed firsthand the resistance to technological progress, from the refusal to adopt metal blades because they were heavier, to the rejection of adjustable pitch designs as unnecessarily complex. Yet each time, Caldwell's data and rigorous testing had paved the way forward, turning skepticism into acceptance. Standing in the oil-stained test facility at Hamilton Standard Propeller Corporation in East Hartford, Connecticut, Caldwell embodied calm determination. With wire-rimmed glasses firmly perched and clipboard in hand, he oversaw his revolutionary invention, a gleaming, three-blade constant-speed propeller that automatically changed blade angles up to 2,400 revolutions per minute. The core of the design was deceptively elegant. Powered by engine oil pressure, a hydraulic mechanism adjusted the blade pitch continuously, responding to flight conditions without pilot intervention. During takeoff and climb phases, the propeller shifted into a fine pitch, like a car's low gear, allowing the engine to reach optimal RPM and generate maximum thrust. At cruising altitude, it shifted to coarse pitch, maximizing fuel efficiency and speed. Most crucially, if an engine failed, the propeller's blades could feather, turning parallel to the airflow to minimize drag and save the aircraft. But changing minds was harder than perfecting the machinery. Aviation's establishment loudly doubted the system's reliability, particularly in combat and high-altitude conditions, where oil viscosity and freezing temperatures threatened hydraulic performance. The Army Air Corps officially classified the design as mechanically unsound. Influential engineers, including air war heroes like Charles Lindbergh, expressed reservations, reflecting the prevailing belief that simplicity trumped sophistication in the unforgiving skies. Yet Caldwell's response was characteristic of a man driven by data over dogma. Faced with resistance, he intensified his efforts, designing and conducting elaborate tests to simulate combat stresses, extreme temperatures, and altitudes beyond operational limits. His whirl test, mounting propellers on a fixed stand to measure endurance and strength, produced results that silenced many critics. Constant-speed propellers consistently outperformed fixed-pitch models in static thrust, climb rate, fuel efficiency, and overall reliability. Behind the scenes, pressure mounted. Pan American Airways and United Airlines demanded solutions to pressing performance issues, threatening contracts and futures. Boeing's fleet of Model 247 airliners was grounded by the inability to clear mountain ranges due to fixed-pitch propellers optimized only for specific flight conditions. The stakes could not have been higher, not just for companies, but for an entire industry at the precipice of transformation. As Caldwell pushed forward, bearing the weight of skepticism and industrial inertia, his invention was poised to leap from theoretical promise to practical revolution. A revolution that would soon extend beyond commercial flight and into the crucible of war. The next chapter would see his impossible propeller tested not just in labs, but in the skies above continents soon to be engulfed in conflict. By 1933, Caldwell's constant-speed propeller had evolved from theoretical promise to practical reality. Yet the aviation world remained skeptical. To truly prove the design's worth, it needed a test that pushed beyond controlled laboratory conditions. A real-world demonstration that would silence doubters and secure the future of aviation propulsion. That chance came with a call from Boeing Field in Seattle. The revolutionary Boeing Model 247, America's first modern airliner, was stranded at Denver Municipal Airport because its fixed-pitch wooden propellers rendered it almost useless over the Rocky Mountains. At an altitude of 5,280 feet, the twin-engine Marvel struggled to climb over the rugged peaks, a glaring flaw threatening not only the airline's reputation, but also the survival of Boeing's contract with United Airlines and Pan American Airways. Pan American's president Juan Trippe had issued an ultimatum: fix the problem or face losing orders to Douglas Aircraft. At United Airlines, President Pat Patterson nervously awaited a solution that could preserve the future of intercontinental air travel. Caldwell's constant-speed propeller was the answer. Mounted on one of the 247s for a critical test flight, it had to prove that it could deliver better climb rates, higher ceilings, and greater efficiency. Test pilot Eddie Allen, a seasoned Navy aviator, took to the skies on February 15, 1933, for what would become aviation folklore. With the constant-speed propeller spinning smoothly, Allen ascended steadily from Denver's thin air, pushing past 6,000 feet, the altitude that had defeated the fixed-pitch aircraft just weeks before. Then 8,000 feet, then 10,000 feet. Crossing the Continental Divide no longer felt like a heroic feat, but a routine ascent. The aircraft's service ceiling soared to an astonishing 20,700 feet, dramatically higher than the fixed-pitch variant. Climb was faster and steadier, and fuel efficiency improved by nearly 12% during cruising power settings. Back on the ground, Patterson received the test results by telegram. Constant-speed propeller exceeds all performance claims. Recommend immediate adoption for entire United fleet. The results rippled through the industry like a seismic wave. The impossible had been made possible. Caldwell's design had disabled the limitations once imposed by fixed-pitch blades, allowing aircraft to operate efficiently across the entire flight envelope, from takeoff to peak altitude. This breakthrough was not just about commercial success. It was a glimpse of the future of aviation technology. Above, in the skies, it promised American air power a qualitative edge that would be vital in the coming global conflicts. Fast, agile, and efficient aircraft meant better reconnaissance, superior combat performance, and ultimately, air superiority. As orders poured into Hamilton Standard's East Hartford factories, Caldwell's invention moved from laboratory curiosity to the heart of aviation progress. But beyond corporate success and engineering triumph, the propeller was destined to become a critical piece in the machinery that would change history, especially as the dark clouds of war gathered over Europe and Asia. The era of aerial warfare was dawning, and Caldwell's prophecy was about to be fulfilled. While Hamilton Standard's production lines in Connecticut buzzed with activity producing the revolutionary constant-speed propellers, the world's skies darkened with mounting threats. Across the Atlantic, the Nazi Party solidified its grip on Germany, and Japan's military leaders openly plotted expansion in the Pacific. War's looming shadow meant that Caldwell's invention would soon be tested far beyond peaceful airline routes. Back in America, skepticism persisted. While commercial pilots marveled at the propeller's efficiency and adaptability, military officials, especially in the U.S. Army Air Corps, voiced concerns about complexity and reliability under combat conditions. Fixed-pitch propellers were simple and unimprovable, whereas Caldwell's advanced hydraulic system, with dozens of precisely machined parts, seemed fragile and prone to failure at high altitudes where icy temperatures threatened oil viscosity. Major Benjamin Kelsey, leader of the Army Air Corps Fighter Project, voiced a common fear. What if the hydraulic system failed mid-combat? A stuck propeller could steal precious seconds, or worse, cause total failure. Critics argued the complexity endangered lives, making the case that simplicity was survival in war's brutal skies. But Caldwell, ever the methodical engineer, responded not with arguments, but with data. He worked relentlessly to prototype and perfect test rigs that simulated extreme flight conditions. His newly developed world test apparatus subjected propellers to vibrations, temperature swings from -40 to 160 degrees Fahrenheit, and continuous operation far beyond expected combat stress. Understanding that oil pressure was vital for blade angle control, Caldwell ensured the hydraulic governor maintained precision even in frozen thin air. Cold weather tests at 35,000 feet demonstrated superior operation, where thicker oil provided stable pressure and better response. Housing redundancies in the hydraulic system and backup mechanical linkages became central in his redesign efforts, erasing most concerns about total failures. Vibrations, once seen as deadly threats, were alleviated by the propeller's ability to adjust pitch dynamically, avoiding resonance frequencies that damaged older fixed-pitch blades. Caldwell's persistence was a battle against not only physics, but human resistance. Public opposition, pressure from rival manufacturers like Curtiss-Wright, who profited from the status quo, and influential engineers argued that the new system's complexities introduced unacceptable risks. Nevertheless, throughout the 1930s, Caldwell's data accumulated, slowly shifting opinion toward acceptance. By 1934, demonstration flights illustrated undeniable performance leaps. On March 21st, at Selfridge Field, Michigan, two identical P-26 fighters launched side by side, one with fixed pitch blades, the other equipped with Caldwell's constant speed propeller. The result stunned observers. The conventional fighter clocked 8 minutes and 30 seconds to climb to 10,000 feet, while Caldwell's propeller-equipped plane breezed up in just 5 minutes and 40 seconds. Speeds soared from 187 miles per hour to 203 miles per hour, and ceilings extended by several thousand feet. Lieutenant Colonel Carl Spaatz, later commander of U.S. Strategic Air Forces, reported that the propeller's advantages were so decisive that immediate adoption promised decisive air superiority, whispering future victories into the ears of leaders yet unaware of the war's full scale. As Caldwell's vision began reshaping military aviation, Europe's air forces largely lagged in technology. German fighters clung to manually adjusted propellers. British Spitfires and Hurricanes relied on crude two-position models, lacking automatic control that pilots desperately needed. Among these pilots was squadron leader Desmond Cook, who, facing imminent Luftwaffe assaults, understood the difference his Spitfires could make if fitted with Caldwell's propeller. His urgent calls marked the start of a desperate race to bridge the technological gap before the Battle of Britain turned to flames. Thus, the stage was set. While war clouds thickened globally, one man's mechanical elegance promised a path to the skies, a path that would soon become a lifeline for Allied airmen and a nightmare for the Axis. Caldwell's impossible propeller was no longer just an experiment. It was a weapon. June 1940. England's skies were gripped by tension. The Luftwaffe's looming assault threatened the island nation. But over at RAF Hornchurch Airfield in Essex, squadron leader Desmond Cook was preparing for a fight that depended not only on courage but on technology. Cook knew from brutal experience that the RAF's frontline fighters, the Supermarine Spitfires, were at a disadvantage. The two-position propellers limited climb rate and altitude capability, allowing German Messerschmitt Bf 109 fighters to outclimb and outmaneuver British aircraft above 15,000 feet. Intercepting bomber formations required higher altitudes and faster ascent, conditions RAF fighters often could not achieve swiftly enough. The numbers were stark. The original Spitfire needed 11 minutes and 8 seconds to climb to 20,000 feet, while German Bf 109s achieved the same in under 9 minutes. This 2.5-minute delay could mean the difference between engaging enemy bombers before they reached British cities and watching them unleash destruction. Frustrated but determined, Cook bypassed traditional channels and placed direct orders with de Havilland Propellers, the British licensee of Caldwell's constant-speed propeller design in the United States. Within 48 hours, an emergency retrofit program was launched to equip his entire squadron with these revolutionary props. Without waiting for full bureaucratic approval, the conversion was challenging. Engineers labored around the clock at Hatfield, removing fixed-pitch hubs and replacing them with hydraulic, pressure-driven governors that allowed blades to self-adjust pitch automatically across flight conditions. Each aircraft needed rigorous ground and flight testing within tight turnaround windows to ensure operational readiness. On June 15, 1940, the first converted Spitfire rose into the sky from Hatfield. Cook piloted it personally, immediately noticing the dramatic difference during takeoff. The constant-speed propeller shifted to fine pitch effortlessly, allowing a takeoff roll reduction from 320 to just 225 yards. More importantly, the climb performance startled even the experienced pilot. Clocking to 20,000 feet now took just 7 minutes and 42 seconds, nearly 4 minutes faster than his identical counterparts. Cook pushed higher, reaching previously unattainable ceilings close to 39,000 feet, where the thin air frosted his breath in the cockpit despite warm ground temperatures. The tactical implications were profound. Spitfires equipped with Caldwell's propellers could now engage Luftwaffe formations from above, employing altitude advantage and superior energy in dogfights. German bombers and their fighter escorts could no longer retreat to unreachable heights, altering the balance of power in the Battle of Britain. Within 3 days, all 12 operational Spitfires in 65 Squadron were retrofitted. Pilots marveled. Flight Lieutenant Brian Lane noted in his combat diary that it was as if someone replaced our engines with twice the power, finally matching German fighters altitude for altitude. This technological leap rippled rapidly across fighter command. By September, approximately 90% of RAF fighters carried constant-speed propellers, transforming Britain's defense and playing a pivotal role in preventing invasion. Propeller advancement relieved pilots from manual pitch adjustments during combat, reducing workload and processing demands. Freed to focus on tactics and gunnery, pilots fought with newfound confidence and precision. Meanwhile, Luftwaffe pilots struggled with manually controlled blades, disadvantaged by the sudden performance leap of British aircraft. The air war over the British Isles was not only fought by men and machines, but by superior engineering breakthroughs made possible by Caldwell's ingenuity. As waves of German bombers approached, battered but determined British fighters charged upwards with the power of the impossible propeller behind them, a decisive factor that helped Britain stand firm in its darkest hour. The era of aerodynamic innovation was no longer theoretical, but vital, shaping the battlefields of the skies and changing history. Caldwell's achievement had turned the tide, proving that in war, the edge of victory often rides on the sharpest blades of invention. As the Battle of Britain raged in the summer of 1940, Caldwell's innovative constant-speed propellers began transforming more than just fighters. The technology quickly spread across the Allied air forces, underpinning a new era of aerial combat and strategic dominance. Within weeks, all newly produced RAF fighters, including Hurricanes and Spitfires, were equipped with Caldwell's system. Pilots reported unprecedented improvements: shorter takeoff distances, higher climb rates, and greater operational ceilings. The difference was like upgrading from a bicycle to a race car, sudden, dramatic, and undeniable. The benefits extended beyond fighting high-altitude dogfights. Aircraft could now maintain optimal engine performance across a broader range of speeds and altitudes, conserving fuel and increasing range. During long reconnaissance missions and bomber escort operations, This translated directly into more effective patrols, greater survivability, and less pilot fatigue. In the Pacific theater, American fighters like the P-51 Mustang and P-47 Thunderbolt, soon equipped with Caldwell's propellers, gained similar advantages. The fighters could climb faster, reach higher altitudes, and maintain superior energy states over enemy aircraft. This edge was crucial as American pilots engaged Japanese Zero fighters that relied heavily on manual pilot skill to manage their less sophisticated propeller systems. The strategic impact was profound. Commanders realized that the combination of higher ceilings, faster climb rates, and increased fuel efficiency, made possible by Caldwell's invention, allowed Allied aircraft to operate more aggressively and with more flexibility than ever before. They could intercept enemy formations earlier, attack from advantageous angles, and retreat at a moment's notice, all while conserving precious fuel and maintaining superior altitude. Back in the United States, the rapid mass production of Caldwell's propellers fueled the wartime effort. The factories in Connecticut ramped up to produce tens of thousands of units monthly, each a masterpiece of precision engineering, tested beyond battlefield stresses to ensure flawless reliability. This technological leap transformed the image of American aviation from supportive to decisive. Caldwell's innovation directly contributed to the strategic victory, saving countless lives, preventing enemy breakthroughs, and laying the groundwork for the overwhelming air superiority that would eventually turn the tide of the war in favor of the Allies. In the end, Caldwell's impossible blades became more than just aircraft components. They became symbols of ingenuity and resilience, proof that in the crucible of war, relentless engineering and tenacity could forge the tools to shape history. The vast scale of World War II placed unprecedented demands on aircraft technology, pushing innovations like Caldwell's constant-speed propeller to their limits. While the design had demonstrated extraordinary performance gains during tests and early combat, its true trial lay in the brutal conditions of frontline warfare. The hydraulic governor system, central to automatic blade pitch adjustment, had to operate flawlessly under extreme stress. Freezing temperatures at altitudes exceeding 30,000 feet, severe vibrations from anti-aircraft fire and combat maneuvers, and the relentless operational tempo of war. Initial setbacks raised fears. In some cases, hydraulic fluid contamination caused governors to malfunction, leading to propeller blades slowly drifting from their feathered positions. On October 14, 1943, the B-17 Flying Fortress, Hell's Angels, disastrously crashed in a Bavarian forest after the feathering mechanism failed, taking 9 crew members with it. These incidents led to thorough investigations and an industry-wide effort to reinforce quality control. Caldwell personally oversaw the redesign of key components, introducing redundant hydraulic circuits and backup mechanical controls. Testing regimes intensified, with propellers exposed to temperature cycles from 60 degrees below zero to 140 degrees Fahrenheit, contaminated fluids, and stress tests surpassing combat stresses by 50%. Caldwell's personal commitment extended to inspecting every outgoing propeller, blending engineering rigor with a deep sense of responsibility. Over time, the rate of failure dropped dramatically, and the feathering capability, once a liability, became a life-saving standard. Dozens of bombers returned to base with damaged engines, their propellers feathered automatically, significantly increasing crew survival rates. The propeller's dependable performance helped extend aircraft operational range and allowed the Allies to maintain relentless pressure across multiple fronts. Fighters equipped with Caldwell's design surged above enemy aircraft, while bombers maintained formation with better throttle control and fewer mechanical malfunctions. In the Pacific, where environmental extremes were even harsher, the constant-speed propellers gave American pilots a vital edge. The heavy P-47 Thunderbolt outclimbed lighter Japanese Zero fighters, helping shift the balance of air superiority. Reports from the field underscored Caldwell's profound impact. Air Commander General Carl Spaatz noted that the constant-speed propeller was as strategically crucial as radar or navigation technology. By 1945, quality control measures and design improvements reduced propeller-caused mechanical failures to below 1%, outperforming fixed-pitch counterparts and validating Caldwell's mechanical vision in the harshest theater of war. Thus, what once seemed a fragile and complex invention transformed into an aviation cornerstone. Through painstaking engineering, relentless testing, and unyielding dedication, Caldwell's invention not only survived the crucible of war, but became an indispensable ally in securing Allied victory. The propeller's story was stitched into the fabric of aviation history as a testament to the power of perseverance and innovation in the face of adversity. By 1944, the impact of Caldwell's constant-speed propeller was visible in every theater of the Second World War. Allied air forces, once challenged by technological inferiority and production bottlenecks, now flew with unmatched performance and confidence. The technology that had started as a seemingly impossible dream had become the backbone of air supremacy. Each aircraft flying from bomb-ravaged airfields in Europe and tropical jungles in the Pacific bore propellers that automatically adapted to every phase of flight. The advantages were enormous. Shorter takeoff distances allowed deployment from makeshift and damaged runways. Improved climb rates let fighters gain early dominance in dogfights. Higher service ceilings translated into strategic altitude control, and enhanced fuel efficiency extended mission range and endurance. The P-51 Mustang, amongst the most celebrated Allied fighters, owed much of its success to these propellers. Coupled with its powerful Merlin engine, the constant speed blades allowed it to outperform German Messerschmitts in speed, climb, and maneuverability, key factors that tipped the balance in pivotal air battles. Similarly, bombers like the B-17 Flying Fortress and B-24 Liberator could sustain heavy damage, feather failed engines, and continue relentless bombing campaigns deep into enemy territory. Their ability to operate at altitudes beyond enemy fighter reach reduced losses and bolstered morale among bomber crews who knew their lives depended on every component working in harmony. On the ground, the massive factories of Hamilton Standard hummed relentlessly, churning out thousands of constant-speed propeller assemblies each month. Factories had evolved from small workshops to sprawling industrial complexes employing tens of thousands, a testament to the scale required to meet wartime demand. Skilled workers, many trained specially for precision machining, labored to the rhythms of war, ensuring that every propeller met the rigorous standards set by Caldwell and his team. Amidst the roar of engines and thunder of combat, Caldwell's vision was realized. The mechanical heart of American and Allied aircraft powered through skies that once seemed hostile and unforgiving. The propeller had become not just a part, but a symbol of American industrial might, of perseverance in the face of doubt, and of the relentless quest for technological edge. As Allied forces pushed into enemy territory, gaining air superiority over the Nazis in Europe and the Japanese in the Pacific, Caldwell's invention stood as a quiet but decisive force in the vast machinery of war. Historians would later recognize that beyond bombs dropped and dogfights won, it was innovations like the constant speed propeller that saved thousands of lives and hastened the end of the conflict. The skies had been won not by chance, but by the convergence of engineering foresight, industrial power, and the unshakable belief that the impossible could be made real. Frank Walker, Caldwell had not only changed how airplanes flew, he had helped change the course of history itself. With the guns silenced and the war concluding, the legend of Frank Walker Caldwell's constant speed propeller extended beyond its battlefield triumphs. The technology that once faced fierce skepticism had become a cornerstone not only of military aviation, but also of commercial and civilian flight advancements worldwide. As aircraft technology advanced in the post-war years, the principles behind Caldwell's hydraulic governor and feathering mechanisms were adapted, improved, and integrated into new generations of propeller-driven aircraft. The lessons learned during the war about reliability, maintainability, and precision manufacturing laid the groundwork for the burgeoning aerospace industry. Caldwell's dedication to quality control transformed manufacturing standards, introducing rigorous testing protocols and inspection routines that became industry benchmarks. His contributions influenced the design philosophy that performance gains must always be paired with uncompromising reliability, a standard that saved countless lives in combat and peace. Beyond technical innovation, Caldwell's story became a testament to perseverance. His success against entrenched industry resistance, public skepticism, and wartime pressures exemplified how unwavering commitment to science and engineering could overcome human doubt and bureaucratic inertia. Educational institutions highlighted his work, inspiring new generations of engineers to challenge assumptions and pursue rigorous data-driven solutions. His legacy was not confined to a single invention, but became part of a broader movement that shaped modern aviation and engineering culture. As jet engines eventually took center stage in the mid-20th century, propellers did not vanish. They remained indispensable for regional aircraft, transport planes, and helicopters, all benefiting from the technological foundations Caldwell laid. Moreover, his innovations paved the way for modern variable pitch and constant speed systems used in today's aerospace, naval, and even renewable energy applications. The ripple effects of his attention to mechanical elegance and reliability continue to influence engineering far beyond the skies he once sought to conquer. Ultimately, Frank Walker Caldwell's impossible propeller was more than a piece of machinery. It represented the triumph of innovation, the courage to challenge orthodoxy, and the profound impact one engineer's vision can have on the course of history. His spinning blades not only powered aircraft, but propelled humanity forward toward new horizons of possibility. As the smoke of World War II cleared and the machines that had changed the course of history came to rest, the story of Frank Walker Caldwell became a beacon of engineering excellence and unyielding determination. His journey from skeptical beginnings to aviation pioneer embodies the spirit of innovation that defines progress. Caldwell's upbringing and education laid the foundation. An MIT-trained mechanical engineer, he brought rigorous scientific discipline to every challenge. Known for his meticulous attention to detail and deep trust in data, he approached his work with a blend of creative vision and analytical precision. His early career saw numerous battles against industry conventions, from advocating metal propellers over wooden ones to pioneering hydraulic controls when simplicity ruled. His tenure as the government's chief propeller engineer instilled in him the resolve to follow where numbers, not opinions, led. Throughout the 1930s and 1940s, Caldwell's leadership at Hamilton Standard transformed a modest facility into a hub of innovation and mass production. He championed quality above all, implementing exacting standards and personally overseeing testing protocols that ensured every propeller met demanding specifications. Beyond mechanical innovation, Caldwell's work influenced industrial practices and management, harmonizing fast-paced wartime production with uncompromising safety and performance. His efforts created thousands of skilled jobs and established cooperative ties across aviation industry suppliers. His contributions earned top honors, including the prestigious Collier Trophy and recognition from President Franklin Roosevelt. Yet, Caldwell remained humble, driven by a desire to serve his country and advance the science of flight. Today, Caldwell's legacy endures in the principles of engineering that balance innovation with reliability, in manufacturing practices that prioritize quality, and in the continued advancement of aerospace technology. The constant speed propeller stands as a testament to the power of perseverance, creativity, and scientific integrity. In the skies above the battlefields, in the annals of aviation history, and in the humming factories where precision meets purpose, Frank Walker Caldwell's impossible propeller spins on. His story reminds us that behind every great leap forward is a mind daring enough to defy convention and a hand steady enough to turn dreams into reality.